Let us look at several examples of SDP. Remember that SDP was of this form, minimize C transpose X, subject to Fx, which was of the form G plus summation of Fi Xi less than equal to 0, and other linear equality constraints Ax equal to B. Observe that here we have written that Fx is less than equal to 0, but we could have also written this constraint in the form that Fx is greater than equal to 0 or Fx is PSD, and it would still have remained the same convex problem. Not the same convex problem, but a convex problem. Here, remember that we require G and Fi to be symmetric, but we don't necessarily require them to be positive semi-definite. We just require them to be symmetric. Earlier we have seen that lambda max of f of x was a convex function of x. Actually, in the same way, it holds that lambda min, which would be the pointwise minimum of several affine functions of f of x, is a concave function in x. Now, because lambda min of f of x is a concave function in x, a constraint of this form would translate to lambda min of f of x greater than equal to 0, which would be a valid constraint because it is of the form concave greater than equal to 0. So this from the result that lambda min is a concave function, this would be a valid convex constraint, and therefore you would again have a convex optimization problem. And of course you can also look at this fact by observing that f of x negative semi-definite is equivalent to saying that minus f of x is positive semi-definite, and there is no restriction on g and f. So I could as well say that g prime is equal to minus g and fi prime is equal to minus f, so that g prime plus summation of fi prime xi is negative semi-definite from this. So this constraint implies that this holds, and this can be defined as f prime of x negative semi-definite. So this is again a convex constraint in x. So really writing that fx is negative semi-definite or positive semi-definite does not make much of a difference. Those can be converted into each other. There are other manipulations that can be done with LMIs of this form. So for instance, suppose that you have fx negative semi-definite and another, so let's say f1x negative semi-definite and f2x negative semi-definite, then both of these can also be combined and written as f of x. This is one matrix 0 0 f2 of x negative semi-definite. So we can combine these multiple LMI constraints into a single LMI constraint, which involves a matrix of twice the size. Note that this is also a valid LMI constraint because it can be written as G1 0 0 G2 plus summation I equal to 1 to n fi1 and fi2 0 0 and xi negative semi-definite. So this is again of the similar form, just that the structure of G's and Fi's are now different. They are block diagonal. Now several general class of problems can often be expressed as SDPs. So for instance, consider the problem minimize lambda max of f of x. Now instead of an LMI, we are saying that minimize lambda max of f of x. This can be converted into an SDP because using the epigraph trick, you can write it as minimize t subject to lambda max of f of x less than equal to t. Now what does this constraint translate to? So what is the eigenvalue? So this constraint can be written as lambda max f of x minus t is less than equal to 0. So it is actually easy to see that this quantity is equal to lambda max of f of x minus t times identity, because the eigenvalues of f of x minus t times identity are simply the eigenvalues of f of x minus t, right? So this is equal to this, less than equal to 0. So in the LMI form, this problem can be written as minimize t subject to constraint f of x minus t times identity negative semi-definite. Or really you can express it, you can write the same thing, just a different notation, that f of x is more negative semi-definite than t times identity. So this is really a different notation for the same thing. These minimization problems are with respect to x and t. So the objective is really a linear function of x and t, where c would be containing all zeros and the last entry would be 1. So we have seen that the problem of minimizing the maximum eigenvalue of f of x can be written in this LMI form. Next, we have already seen that LPs are actually a special case of SDPs, because we said that if you take the f and g to be all diagonal, then you get an LP, which is a special case of SDP. In fact, it holds that LP, we have already seen this also, so LP is special case of QP, which is special case of QCQP, which is again a special case of SOCP. And it turns out that SOCPs are special cases of SDP. So let's see how SOCPs can be written as SDPs. So let's consider the general form of an SOCP, which is of the form C transpose X subject to AIX plus BI norm less than equal to CI transpose X plus DI. And there can be other equality constraints. So let's assume that there are some equality constraints for now. But what to do about this SOC constraint? So remember that earlier we have seen the fact that norm of x less than equal to t constraint can be written in the form of a positive semi-definiteness constraint on a matrix. So what is that? So you can verify using Schur's complement that this can be written as Ci transpose x plus di, this is a scalar, times identity AI transpose x, AIX plus BI, this is a vector, and AIX plus BI transpose, this is a row vector, and Ci transpose x plus di. Right, so this constraint can be written as this matrix being positive semi-definite, and this is exactly the LMI form, because you can actually find out what is G in this case. So what is G? G is all the terms that contain constants. So G would be of the form di and bi transpose here and di times identity. So that would be G, and then Fi or Fj would be of the form Cij identity, Aij transpose and Cij. So that would be Fj. So you can verify that this is indeed of the form G plus summation over j equal to 1 to n xj Fj is positive semi-definite. And we have already seen that this, by writing G as minus G and Fj as minus Fj, you can write it as some matrix, some LMI less than equal to 0 or negative semi-definite, which is the standard form for a SDP. So we have actually proved that general SOCP is a special case of SDP. So SDPs can be more general form also, and SOCP is a special case. And because SOCP is the most general problem that we have seen so far, so all the problems that we have seen, all the special problems that we have seen are subsumed into SDP. Other than geometric programs, those are different. So problems involving log or x are different. So other than that, all the problems that we have seen are special cases of SDP. The Schur's complement is actually very useful in manipulating all sorts of problems. So let's look at an example. Let's look at this example. We are minimizing C transpose x square divided by D transpose x. Now, so let's say that subject to Ax equal to B. Now, through the use of epigraph technique, actually you can convert it into an SOCP. So let's write it as, let's apply the epigraph trick anyway. So let's write it as C transpose X square less than equal to T times D transpose X, and then AX equal to B. Now instead of converting into SOCP, we can also apply the Schur's complement result here. So we can observe that we can write this as, so remember the Schur's complement formula and observe that we can write it as T C transpose X, C transpose X, D transpose X is positive semi-definite. Note that this is a 2 cross 2 matrix. So its Schur's complement is exactly T times D transpose X minus C transpose X square. So this problem also, in the same way, we can express it as, so we can say that minimize T subject to AX equal to B and subject to this LMI constraint. So it is very easy to convert this problem into a SDP through the use of the Schur's complement. Let's take another example, which is the L2 norm minimization, where we are talking about not the vector norm but the matrix norm. So let's say that we are considering minimize over X L2 norm of f of X. Now what is the L2 norm of f of X? Remember that the L2 norm of a matrix was given by the square root of lambda max of A transpose A, because it was the maximum singular value of A, which is this. So how do we convert this problem into an SDP? So let's apply the epigraph trick. So we obtain minimize over X and T fx L2 norm less than equal to T, and this constraint is really saying that lambda max of fx transpose f of x is less than equal to T square. Now let's manipulate this constraint a little bit. So let us write this constraint as lambda max of fx transpose fx minus T square times identity is less than equal to 0. And we already know that this constraint can equivalently be written as fx transpose fx minus T times identity is negative semi-definite. Now we already know this, but this is not in LMI form, but we can convert it into LMI form, and this can be equivalently be written as T times identity minus f of x transpose T times identity inverse f of x. So I'm assuming that these identities are of the correct size. T times identity inverse is simply T inverse, because identity gets multiplied and removed. So this is greater than 0, or this is positive semi-definite. This is still a matrix, and if you consider this as a Schur's complement, then this would be equivalent to saying that T times identity f of x transpose T times identity is positive semi-definite. And of course we have assumed here that T is greater than or equal to 0, or T identity is positive semi-definite, which is equivalent to saying that T is greater than or equal to 0, and you can see that this is a LMI. So we have been able to write this constraint, which did not look like an LMI, into this form, and therefore the L2 norm minimization of f of x is also a SDP. So again here Schur's complement is the one that allowed us to write in this way, and a similar problem in this context is actually minimization of ax plus b transpose f of x inverse ax plus b, and subject to constraint that f of x is positive semi-definite. So this part is already LMI constraint, but we need to worry about the objective also. So we use the epigraph trick and write it as minimize over T ax plus b transpose f of x times ax plus b less than equal to T, or T minus this thing inverse is less than equal to 0. Right? These are all scalars now, and we already know that this is of the form which appeared in the Schur's complement. So this becomes f of x, then ax plus b transpose and T is positive semi-definite. So again, which is of LMI form. So problems which may not look like LMIs and which may not look like SOCPs either can actually often be converted into LMI form. So this SDP is actually a very powerful framework, and a very wide class of problems can be converted into SDPs.